from the problem, it's always easier in physics if we are able to imagine what is going on in the problem. So we always start with a sketch. So from the problem, we could represent the first charge to be this one, and we call this Q1. And we also learned that Q1 has a positive charge equivalent to 25 nanocoulomb. Right. And another charge in space, we call it Q2, is located here. That's negative 75 nanocoulombs. And the two charges are separated by a distance of, based from the problem, a distance of 3 centimeters. Okay. Now we're tasked to find for these quantities. The first one is the force that Q1 exerts on the second charge, and then also we're looking for, or we're tasked to find for the force that the second charge exerts on the first charge, on Q1. Now I know this problem is very easy, but I would like to point out or highlight certain things which will be important when we try to deal with charges now that are quite complex in orientation other than this one. Now in this problem, we have to tackle about the key physics principles that we will be encountering in this problem. The first one is this. The first is we have two charges, 2-point charges separated in space, and we know that the force of interaction between charged particles is given by the Coulomb's law, which is expressed as K. And I would like to emphasize the Coulomb's law, you can only get the magnitude of the forces all over r squared. So that means the Coulomb's law will actually tell you of the magnitude only. That's why this is in absolute value. The second thing that you have to understand is the nature of the forces between the two charges here must be an attractive force, right? It should be an attractive because of the fact that they have opposite charges. And this is just your law of electrostatics in action. Electrostatics. All right. And the third one is this one. These charges are actually obeying your Newton's third law, which is your action-reaction force pair. So Newton's third law. So these are the physics things that we have to consider in solving this problem. All right. So I think we're now almost ready to solve for the first force. Maybe I'll use blue. All right. So the first that we are going to solve is the force that Q1, this particle right here, exerts on Q2. Now, to solve that one, we have to understand something about how it's phrased. Q1 and Q2, force of Q1 and Q2. So this means that Q1 exerts a force on Q2. So for us to know the magnitude, for us to know the direction of that force, we start with the charged particle which like receives the interaction from Q1. So that's Q2. So Q2 right here bears a negative charge, and in response to Q1, it will be attracted. So that means that the direction of the force is towards the left. So that should be the direction of force of Q1 acting on Q2. That right there. So this is telling us that the sign of this one, because of the convention that we're following, must be negative, right? So from here on, it's quite very simple to follow because we simply have to employ the Coulomb's law. So this will be just K, and then the first charge, the second charge, all over the separation distance squared. Simply substitute the values. So the Coulomb's law is 9 times 10 to the 9. The units is Newton times meter squared per Coulomb squared. And then we simply substitute the charges. Q1 is 25, and remember your prefixes, nano means times 10 to the negative 9 coulomb, and then your Q2 is negative 75. So note I still wrote the negative there, but it doesn't have any effect because we take the absolute value all over r squared. Now take note this is in centimeters, and I'm hoping you can remember that you can just write that as 3 times 10. Cinti is a prefix which means 10 to the negative 2. So you have 3 times 10 to the negative 2 meters. 3 times 10 to the negative 2 meters. And please do not forget that that quantity is actually squared. All right. So looking at the units, it's quite apparent that the m here will cancel out, and the c times c will result to c squared, which will be canceled out by that unit, and we end up with Newton, which is a sensible unit, of course, for a force. And after plugging it in your calculator, you'll get that the force that Q1 exerts on Q2 according to the Coulomb's law is simply 0.01875 newtons. And considering its direction, because as I've said, the Coulomb's law will only tell us of the magnitude. So from the illustration above, it's quite apparent that that force must have a negative sign, implying that it's directed towards the left. Okay, now that's the force that Q1 exerts on Q2. So we're done with this one. We are going to solve for B, the force that Q2 exerts on Q1. So basically what that equation would entail is simply we have I don't know if I can erase this one. Yeah, we simply have to change something. But from the looks of it, it's going to be Q2 and Q1. And going back to the illustration, again, the same logic, Q2, the charge to exerted on Q1. So we start plotting the direction of our force on Q1 because Q1 will respond a positive charge. How will it respond to a negative charge? Obviously, that will be attracted, so that force should be directed to the right. So we have a clue that this force now, I'm simply recycling what I've written. The force of Q2 and Q1 must bear a positive sign because the direction of the force is actually towards the right. And that's the usual convention we are doing even in your math. Now, simply we have changes in the order of this one, sorry. This will just change. So this will be Q2 and this one will be Q1. But then again, we learned from math that multiplication commutes. So this will just exchange its place, but nothing really happens on the on the product of the two. So we practically get the same process of solution, except that we merely have changes in the position of the variables. And then what's interesting here is that we get the same magnitude, but this time around, the force that should put Q2. Sorry, I'm quite new to this DIY lightboard thing. Yeah, force of Q2 on Q1 has exactly the same magnitude, but it has a positive sign. It means to say that Q1, the force that charge 2 exerted on Q1 is towards the right. It's basically attracting this object. And going back earlier, the force that Q1 exerts on Q2 is towards the left, which tells us that Q2 is being attracted to this one. And that is quite what I've said earlier, that the force is attractive because of the opposite nature of the sign of the charges. And that's basically what is said by the law of electrostatics. Okay, now basically we have solved everything now right here. So I'm just going to recap everything and tell us something how it obeys the thing that I've written there. It tells us that the force that Q1 exerts on Q2 is simply equal to negative 0.01875 newtons, and the force that Q2 exerted on Q1 is simply the positive of 0.01875 0.75 newtons. All right. Now, if you can see right there, um, this is actually what I've been talking here. It obeys the Newton's third law. It means to say that they have, you notice, a same magnitude of the forces, but you got opposite directions. That's why you get a varying sign. One is positive and one is negative. And a very important question is to realize that even though 25 nanometers and 75 nanometers, one is larger than the other, you don't get to say that because it has a larger charge, then it must have experienced or exerted a larger force on the other particle. No, we cannot say that because of the fact that this obeys Newton's third law, and truly, the if it obeys Newton's third law, the force is truly a result of the mutual interaction. So no object or no charge is exerting larger force or smaller force just because it has a larger charge. It doesn't work like that. So the force that they have are the same magnitude, but it acts on different direction regardless of who gets the larger charge and the lesser charge, just like what you learn in gravitation.